Hello, everybody. Today I'm going to talk about neuromorphic design based on our architecture, reconfigurable, event-based system, and using RSTDP, reward modulated spike time independent mass-gathered learning algorithm. Neuromorphic high-performance computing. Let's say why we need such a system. There are billions of devices which are connected to the clouds and internet. For example, self-driving autonomous cars generate 4 terabytes of data per day, and there are a lot of sensors that should communicate to each other in real time. Therefore, we need a big and powerful computing platform that could deal with those big data that an autonomous driver could, to be able to drive safe on a road, should do 5 exaflop per hour. It means 5 multiplied by 10 power 18 floating point computing steps. Therefore, the high-performance computing with neuromorphic solution come up with leveraging distributed parallel computing, which is able to learn in real time with online and on-chip learning to dealing with those sensory data. For example, if there is a system on chip puzzle with GPP, FPGA, GPU, the neuromorphic accelerator unit would be the missed piece of this puzzle that could be added for cognitive computing. But what are the main differences between the traditional VS versus neuromorphic computing? If you have a look at the Feynman architecture, there are complex cores which are very fast, but they are connected to the slow hierarchical memory. It means that it takes ages from CPU point of view, that data come from peripheral memory to the main memory, then to the shared memory to the local memory, and go back there. That we call it memory bottleneck or Feynman architecture bottleneck, which we don't have it in spiking neural networks inspired by brain computing, which we have 2 simple cores, which between them is simple memory, which is very fast and efficient and retrieving data there. Let's talk about our architecture, POET's neuromorphic system. There are large-scale neuromorphic projects which POET could be part of this community. For example, Louis from Intel, Human Brain Project, has Spinnaker large-scale neuromorphic system, as well as BrainScale, TrueNor from IBM, and NeuroGrid from Stanford University. POET stands from partially ordered event trigger system, which is a project between Imperial College, University of Cambridge, Newcastle, and Southampton. From technology point of view, if we have domain-specific architecture here as an extreme, which Spinnaker could stand here, and if we have parallelism here, which GPU could stand here, the POET would be somewhere between those 2. But let's have a look to the architecture of POET. POET is extensible and extendable. It means we can add more boards and more boxes. But the current version, we have 8 boxes. Each box has 7 FPGA board, which 6 working FPGA and 1 interconnection FPGA between the desktop computer and FPGA board. But in general, we have more than 3,000 processing cores and close to 50,000 threads. What is inside a core? We have tensile soft-core overlay. We define 1 FPGA to 16 tile. Each 8 tile is connected to 1 off-chip RAM, and each 4 tiles is connected to 1 SRAM. But what is inside a tile? Inside a tile, there are 4 cores. Each cores could support 16 threads for 16, for example, parallel way of computation, like 16 neuron could be computed in parallel way, which each 4 cores has 1 mailbox and 1 floating point unit. But let's have a look how we map the spiking neural network to this POET hardware. The POET works based on the graph theory. In graph theory, we have nodes like Vx, Vy, and we have the edge between the nodes and the message that communicate between the nodes. Here, neuron could be the vertices or nodes, synapse could be the edge, and spikes could be the messages. For example, if we have 2 spiking neuron, we can assign each of those to a thread, neuron X for thread X and neuron Y to thread Y to do the parallel computing. If we have bigger network, still we can assign them to the core on tiles, or if we have millions of neurons, we can assign it to 1 box or 8 boxes still. So the first example for training on POETs, we have done what with MNIST data set. MNIST is bunch of 60,000 of data, for example. Bunch of 2 is here. We apply to the neural network 2, and we expect that the neural network could recognize properly the number. Each MNIST number has 28 by 28 pixels. Each pixel has its own intensity. For a spiking neural network, we have to transfer those intensity to the spikes. For example, if it's completely black, it would be 0 intensity and it is completely white, it would be 255, and we transfer those intensity to a spike. For example, here we have one demo of what we have done with MNIST on. Here we read the data, and those numbers are intensity of each number that you can see. Going back to the. Okay, let's have a look to the challenges that we have to run a spiking neural network output. We have here we have a look to different synchronization, but why we need synchronization for event-based platform, which are asynchronous? Because we need to get sure that every spikes and every messages from previous times that has been handled and there is no missed one. So we need kind of a state machine-based synchronization. We define 3 and check those 3 to see that which one is work better on our system. Clock-based synchronization, that we define a clock devices to check the internal state of the neuron, and whether the neuron do firing or not, it will check in any time step. So it could be very slow, but very accurate. The second one is GAS, globally asynchronous, locally synchronous. We don't have global clock device like previous one, but we have the local things. It means that each neuron, for example, should check that how many input it has, and we need to define a counter in each neuron to check the number of the input spikes. And the last one is hardware idle detection synchronization algorithm, that we do this with defining a synchronization barrier which produce hardware signals. When there is no pending message on system, it will produce those signals to get ready for the next steps or time steps. For training, as I mentioned, we use reward-based training, which is inspired by biological brain that use dopamine in the system. Here we use STDPs by time-independent plasticity, but we add the reward and punishment to the system. But what are the advantages of adding these reward-based things to the STDP is that it's simple because we have still the local learning, which is the nature of the STDP. But in STDP, we can get the frequent feature and recognize them. But for rare, the STDP doesn't work perfectly. Adding these reinforcement learning things could improve that things, and also we hope that it could improve the accuracy of the recognition. And the system, we also have a look for the communication. We also have it to the unicast and multicast. Unicast, it means that each thread will communicate with only one thread, and in multicast, one thread could communicate with several threads. We define the programming routers, and we define the cluster-based things, and we predict that multicasting could be quite faster than unicasting. And here we have the result to check our prediction. For example, as expected, the clock synchronization is quite slow, running on POETs for 1 million number of the neuron. And as you can see, the second one would be GALS, and the fastest one would be hardware detection. That with hardware detection, we could simulate 2 million of neurons. For comparing the multicast and unicast on the system, as you can see, for small number of the neuron, the difference is not that much. But if we go into 1 million to 2 million, the speed could be even double faster. Have a look to the accuracy without tuning anything and using spiking neural network, a shallow neural network. Using only STDP, we reach to 89.7% of accuracy, and using our STDP, we reach to 91.4% accuracy. But we check also other kind of accuracy, which might be interesting for spiking neural network community, which is a spiking activity. We want to check that how accurate one neuron could do the spiking and could fire. And we compare it with Brian as a reference, and we reach to 96.1% of accuracy. And here you can see the raster plot of Brian and POET next to each other. Okay, and here we have the POET's speed comparison with Brian and Spinnaker. If we have a look to the number of neuron, we could do 2 million of neuron and run it on POETs. And comparing the speed with Spinnaker, I can say that POET is between 8 to 16 times faster than Spinnaker, and between more than 25 faster than Brian. Okay, and what a conclusion and take-home message, I can say that FPGA approach and FPGA-based platform could be quite promising for neuromorphic platform, hardware platform, high speed and parallel computation in FPGAs, and high speed communication, more than 300 gigabit per second internal connection speed. And then the hardware using the software as we used in this research, for example, could make the programming problem with FPGA easier, as we can use the high-level programming like C and Python. Using appropriate synchronization method as an event-based system has a significant impact on the speed of the neuromorphic system. It means that the hardware idle detection had the best performance on the system. And the reinforcement reward modulated STDP learning has a great potential for online on-chip learning using the real-time sensor data on the spiky neural network system. Thanks a lot for your attention, and I would be more than happy to, if there is any question, to reply.